Hello YouTube viewers, welcome to my show Future Friday. In today's episode, we're gonna discuss about future of spacesuits. So let's dive right into it. Now you have to understand it. I have already done a detailed video about the spacesuits that we have right now. You can check that video out here, and I'm just gonna give a quick overview of that. Basically, vacuum and space kills us. Flat out. There is no discussion, there is no discrimination here. You die in vacuum, that's it. Now we need a lot to survive. It's not just like, okay, vacuum because you cannot breathe, you're gonna die. Okay, so now you have oxygen, everything good. No, we need multiple layers of things in order to survive. Now primary of those is pressure and thermal. Because we evolved on earth, we evolved to handle 1 atmosphere, aka 1 bar or 15 psi of pressure. Every system in our body is designed to work at that temperature. Now again, it can handle some range. Let's say you lived in a place of like very high altitude, like mountain range and all that. Again, your body can still manage it, but we have to have some pressure. It cannot be 0 psi. We have to have some pressure. Ideally, you must be around 10 to 7 psi. So we have to have pressure just for our body circulatory system, for our basically core existence to work. And then we come to the thermal aspect. Now earth, the sole reason earth is not cooked is because it has a dark side, basically a night side. Now how the heck that makes sure that we do not get cooked? Think of it this way: we have an atmosphere, so sun is cooking us on the day side, but because of our atmosphere, the energy is being distributed in a large area. Now we have a hot side that is facing the sun, we have a cold side that is facing the absolute vacuum. So benefit of that, our heat gets distributed. So atmosphere is acting as a buffer. Because of this buffer, the temperature is like fluctuates very little. Now if you are not exposed to this buffer and you directly are like in space, let's say this guy without the spacesuit, the thing will happen is that the face of you that is facing the sun, basically be it back of your head or front of your head, will be cooked by third degree burns. Like you can have as high as 150 to 175 degrees Celsius on the side that is facing the sun. Now here's the funny part: the other side that is not facing the sun, basically let's say you have a hand and this side is like the face that is facing the TV will be burned to 150 degrees. The face that is facing on the vacuum basically, and the quote unquote shadow, it will drop to minus 150 degrees Celsius. So basically you're not only gonna have a third degree burn, you're also gonna have a frostbite on the other end. So we need very serious amount of pressure management, and we need really good thermal systems. Now on top of that, we also have to make sure that we are adding oxygen, because it's not like we breathe a very little amount of oxygen. We breathe a lot of oxygen, so we have to have oxygen. And then becomes the tricky part is we have to remove the CO2. CO2 is not only like a bad gas, it's a killer to us. Basically, if you are breathing air that has like, let's say, 5 to 10% CO2, you already starts to act like dizzy. At if it exceeds 10%, you are in danger zone. If it exceeds 12%, you are at serious risk of dying. If it exceeds 13 to 14%, you're dead. So you have to understand that like it takes a lot of things to make sure that we can survive this space. Now we can survive it, and we have a spacesuit, of course. That's the whole reason we have this kind of photograph. Then what's the problem with this architecture? If it works, there's an old saying, if it ain't broke, don't fix it. So what's the problem with this? Well, the primary problem, they are ludicrously expensive. I'm talking about $5 million per piece at bare minimum. So you have to understand, like, it's ludicrously expensive. Like, to give you a context, like you can send rocket missions now at that cost. So flat out, it's a very expensive aspect. Then the another aspect that makes it even more difficult is that we do not mass produce it. Even though for entire space project, a new suit design was selected. So that suit was we learned from Apollo mission, and we learned from Russian missions and all that. So we realized that we can make spacesuit in chunks. Basically, you will have a torso chunk, you will have arm chunks and all that. Like you will make it in chunks. So but again, the chunks will be tailored, fitted to each other. Basically, like you will have a chunk that is for this guy, this another chunk would be for different number size. Basically how we have shoes, different numbers of shoes. So that way people tailor the suit for the astronaut. So let's say you have an astronaut Sunita Williams, and she will have a specific suit that is tailor made for her, even though it is like taking the off the shelf part. But you have to understand that off the shelf is like $1 billion self. So based on that, her suit is made. So if somebody else tries to wear it, he will have very difficult time. Or like a man is there and a woman is there with a significant enough height difference, their suit will simply not work with each other. So you have to understand, we have to make a general purpose spacesuit if you want humans to colonize Earth, not just astronauts, not just guinea pigs and all that. Like people to live there, to work there, we have to have a suit that is like this is a spacesuit, that's it works, no discussion about it. Now, or on top of that, let's say that itself is not an issue. You're like, hey, I can I can take care of the trailer mid part. The final aspect that is really painful for us is that it is very heavy, 150 kilo. Now you may think, okay, it's in zero gravity, so why the hell I care? Here's the in zero gravity, you do not have to worry about your gravity based acceleration on your mass. Basically, you feel weightless. However, your inertia is exactly the same. So to give you a context of this, think of this way: the person inside the suit is 100 kilo, just go with that, but the suit is 150 kilos. So what does that mean? Basically, if this guy is running, his muscles have to handle the inertia of around 250 kilos. His muscle, like if he apply, like let's say he's running, okay, he got the acceleration, he's running, and then he's like, okay, I'm gonna stop. Now the moment he tries to do that, his body has to withstand the shock of basically 250 kilos. So that is why we want to make it light, and it also affects other things. Let's say you have a basically extravehicular suit with thrusters, so you can move around and all that. The thrusters have to be powerful enough to move 250 kilos, not a 0 gram. Like it has to add acceleration to that, which is very easy, but when you have to apply brakes, you have to apply brake on 250 kilogram object. So you want to make sure the suit is as light as possible. So this weight, even though quote unquote weightless, still adds inertia. You want to make sure that it is minimized. And not to mention 150 kilo, that's like if you're sending 14 astronauts, you are sending like a like you can literally double the number of astronauts if you don't have to send such heavy suits. Now, current design, the design that we use, all of them, including the SpaceX Starman design, they are all what we can classify as air bladder system. We simply cannot go into the future with this design. Like again, this is a very good design. This is what got us, off the ground in the first place. But again, now we have to move to something better. So this no air bladder design we have to go with. Now, what is the problem with air bladder? Like it has been working for 50 years. So what's the problem? The problem is very heavy, because you have to understand, it's just like a balloon that people have put around you. So that balloon design is very heavy because the fact of the surface area has increased, because you now literally have multiple inches of space everywhere. So your volume has increased, so flatter mass has increased, and there is air, pressurized oxygen into it. So that also adds weight. So it is very heavy. Side effect, again, that inertia issue happens. Then it's very hard. Now what do I mean by hard? Basically, it's very difficult to operate because you are operating a thing from inside. You are inside the spacesuit, and it's like if they pressurize to 15 psi, it will be like locked like this, like a football. Basically, you will be completely locked like to move fingers and all that. You have to like because you have to understand, when you have that much pressure, it's like it want to be taut as much as possible. So for this reason, we do not want to have high pressure. So, and again, even with pure oxygen environment, we can only reduce the pressure to 7 to 8 psi. That by default makes the spacesuit very fatiguing. The astronauts, that's why astronauts are so fit. They have to be fit, otherwise they will simply not be able to use their gloves in the space. So it makes it very difficult, the bladder design by default. And it's leaking. Now you might be like, wouldn't that kill the astronaut if it was leaking? Well, everything leaks. That's the first reality of reality. Everything leaks. Although if you follow the documentation of basically SpaceX validation, what NASA required of them for their in-vehicle spacesuit, is they will be like, it won't be like it should be leak proof. It will be like it should leak within a tolerant range. Basically, if the suit is exposed to pure vacuum, raw, absolute pure vacuum, it should leak, let's say, in 1 month to 1 month to reduce to 1 psi. So that's the requirement. You will never design a suit that's like, it does not leak. Of course, it will leak. The question is how much and how quickly. So we'll always have to worry about leaks. So is there a better design? Is there a better physical reality, not just some sci-fi hoo-ha? Because you can just have Iron Man suit and like tick tick done. If you can't do that tick tick done, so you have to go to this. This is the MIT based design, MIT biosuit. Now benefit of this design, it's skin tight. Basically it's a third skin to you. Basically it's like a skin on top of another skin. Now benefit of this design, it does not rely on air pressure to compress you. It relies on elasticity. Now how it's doing that is very clever. If you find the high resolution images of that, you will notice there is a lot of threads going around. Those threads are metal threads, so basically they will never expand. So you're like, wouldn't that person will be like talk like this? No, because the threads, the engineering done here is the interesting part. They found out there are certain lines you can draw on human body that will never change. Basically, let's say I draw a line here, a figure 8 to my elbow. Now this figure 8, let's say if you unfolded the figure 8, it's 12 centimeter, it will remain 12 centimeter whether I do this or this. These are what they call non-expanding lines. Every non-expanding line on human body will have a thread taut around it, so that way you can apply pressure without restricting the movement. So this has been built, has been tested to some extent, and the first impressions are very simple. Like if Apollo suit will require, let's say, 100 watts of energy from you to move and do all that, this will require 25. It's tangibly much more better, and this is like feasible enough. You can have like 13-14-year-old children to do this, because you have to understand, like every time I'm seeing, like, space colonization, nobody talks about the children. It's like they also have to figure out how to handle spacesuit. So again, one TV show did figure that out, but you have to, like, normal pressurized airsuit, children will just get exhausted because it's literally difficult. So this suit takes care of that, and because it's so skin tight, it's literally the weight is reduced and fatigue is reduced. So astronauts can actually work for 6 to 8 hours, not just like monitoring, removing a bolts and heavy work. I'm talking like, let's say they want to like build a new habitat, something big, expensive, energy intensive thing, they can do that because it will reduce the fatigue. And it's smaller and agile. Smaller simply because it's like much more closer to your skin, and agility is a very important part. Because of this reason, because our current suit is not agile, we have to deal with two suits. Basically, every time in space shuttle history, whenever an astronaut was sent, two space suits has to be sent with them. Basically, orange suit, which is flight suit, and then the space suit. Problem with that is, like, because ideally you want only this, because again, this is redundant. And the problem with this design is so big, so clunky, that people can't use this inside the space shuttle. Basically, they won't be able to hit all the switches. Even though switches are so big and, like, physical, tactile and all that, this is so hard to use inside that they are flat out like, yeah, we can't use that. So they created this design. So think of it this way, this is just there to as a placeholder. It's like if you had this like during basically launch and all that, there is nothing that can happen to this, because this has umbilical cord. If you pay attention to the launch videos of old space shuttles, you will see people are carrying the, like, briefcase connected to the umbilical system. Now, umbilical system is like what's providing them the oxygen and life support. This has its own internal life support. Basically, this is classified as spaceship for one. So if space shuttle fails for some reason, let's say some electronic failure happens or something happens, this suit is wholly reliant on hoping that life support systems are working, because something happens, let's say some damage happened and all that, their umbilical gets destroyed, yeah, they're dead. So you have to understand, this is just a placeholder for us. We don't want this, nobody wants this, it's just we can't do anything about it right now. So the intravehicular activity spacesuit, they have to go. We cannot go into future and, like, space colonization while still relying on that. So if you see Boeing spacesuit, that's intravehicular. Basically, what happens if you put this to space? Nothing. Like, it can easily survive the vacuum. Then why it's not a spacesuit? Basically, the moment sun touches this, basically it comes out, let's say, out of the shadow. Yeah, it will be cooked. The person inside will be cooked. And not to mention, it requires an umbilical. Basically, there is a physical pipe connecting everything. And not to mention, this also adds waste, like weight and cost. So you can understand, like, space shuttle, if all you had to do is like take people, send it to ISS, or that's all you have to do. Just by removing these two suits, you can add like almost 2.3 times of the total count. So you can send upwards of like 20 people. So that is why we have to change this architecture, where it's like, oh, we have in SpaceX like that star mentioned, that's also an intravehicular activity suit. It's not a suit that you're supposed to wear outside. Nothing will happen to you, it's just you will be cooked from inside and freeze to death after that. So how the heck we gonna do that? Again, ideas are good and everybody wants to do that. It's just how the heck you gonna do that? Now you have to understand, this is one thing that I respect about Elon Musk, is like he realized that during 1960s and 1970s, everything in space industry was going through breakneck pace. Like every Tom, Dick and Harry was doing it, from Britain to France to Soviet Union to America. Everybody, Tom, Dick and Harry was like, going at it. So technology development was like, now, what happened after the space race was concluded, once America landed on the moon, is like everything was stopped. Like literally the amount of money that went into R&D, they were zeroed out. And people did not, like, what's the point? They lost their drive. So that is why when Elon Musk starts to rocket his company, that was his epiphany. Like when he was returning from being rejected from Russian military or Russian cosmonaut, and they were like, yeah, we want to use your SpaceX was like, hey, I want to use your rocket to, like, send a greenhouse to Mars. They laughed him out of the room. So during his return, then he realized, like, after studying a book, he's like, wait a minute, all of them are like entirety of planet Earth, basically space industry is relying on the engines that were built in 1970. So he just throws everything out. So like, okay, let's start from scratch. That's gave us the Merlin engine. So same can be done here, because you have to understand, space suits that we are using, they are coming from Apollo era. Again, lot of improvement have been done, refinements, position, like it's been polished, but not new. but we have new materials now. These materials flat out did not existed 50 years ago, like aerogel. And when I say aerogel, you have to understand that there is not one type of aerogel. Aerogel is quote unquote material. You have to alloy it. So this is like the lightest alloy if you want to just insulation. Now again, if you want to make a suit, you will make it much denser than this. You will not make it 99% air. You will make it, let's say, 80% air, depending on your requirement. So we can alloy this with much more advanced insulation. Spacesuit primary function is insulation. So if you can have an insulation that is like, let's say, only 1 centimeter thick rather than 1 inch thick, that saves you a lot of money, effort, time, everything. And these are very resilient, especially in certain alloys. Normal aerogel is weak, like you drop it, it shatters. You put water on it, it gets destroyed. But alloyed ones, they are indestructible. So we got the insulation material. Then we got this graphene. You have to understand, if you cover a person in insulation, he's gonna cook to death. So how do you make sure that you don't cook your astronaut to death? We have to have solid state thermal pads. Now, due to the advancement in computer industry, a lot of people started to invest money in thermal pads. You have to understand, right now we have liquid pumps, basically water being circulated. Problem with that, it leaks. And this did happen in orbit, that one of the astronauts pipe broke and it started to leak. And like, here's the deal, because of the zero gravity, it was leaking based on capillary action. So it was covering his whole back head, and it started to, like, at that point he was so close that if his nose was covered, he would flat out suffocate to death. So that happened. Like, water is not that friendly. Like, it's not like, oh, leak happened, it's like pooling up in my boots. It could leak up anywhere. So this layer, that LCVG, basically water tubing garments, we have to remove that. Not only it adds bulk, it requires a water pump to circulate it, and it's very dangerous. We have to use solid state. Again, benefit, nothing will break. And all we can do is like dump the energy collected from this. How? That's up to us. Like, we can literally utilize on normal old radiator system, or we can use Peltier systems. So these advancement allows us to actually shrink the technology. Like, you have to understand, like, it's like if somebody said, hey, I want to make 4G technology in 2G era, you can't do that because silicon was not good enough. Now we have the now we have the technology. So that's why basically we want to make as solid state as possible. You just wear it, that's it. We want to make it solid state, no liquids, no moving parts, reduce the moving parts number as much as possible. Now all those I specified, like, spacesuit is not that difficult. It's just the life support that goes behind it that's difficult. Now, what's the problem with that life support? Well, we can make very good life support. Right now we have the technology to make a small enough RO purifier that you can literally on a person purify his urine and make it water, like portable safe drinking water. Right now we have the technology. Problem, it requires a lot of electrical energy. Our lithium ion batteries is just not good enough. Right now our batteries only have spacesuit batteries have like 300 watts of power, more or less. So that's okay. That's okay for 6 to 8 years. Years, I'm saying 8 to 8 hours maximum. But you have to understand, like, if you want a spacesuit that is put and forget, like, you don't want a spacesuit because it's a critical component. Let's say you are working inside a space station, a breach happened. You have to wear the suit. You're not gonna be like, hey, double check whether the battery is there or not. So what can we do? Well, due to recent advancement in silicon industry, we have advancement in beta voltaic batteries, basically nuclear battery. You can check my video about that here. Now these batteries, right now they are very low power, but people are like, science is there. Science is like, yeah, you can make it much more powerful. So if we reach a point where we can truly utilize this, you can have a life support system that simply does not have to worry about anything. Basically, you are urinating, it's just taking care of the water. It's like distilling it. You are sweating, it can extract that also. And like, basically you can power everything. You can make sure that if the person is wearing a spacesuit, the only thing that will end him would be hunger, not the air, not water. Because you can even split CO2 if you have enough electrical energy. So that's the whole point. And if you have these batteries, they have right now, the one that we can buy right now used in pacemakers and all that, they have battery life for 50 years. So like, if you have a suit, it's gonna work. You don't have to double check whether the battery level is there or not. So these two technologies, the fact that we can have now much better insulation, the fact that we can have solid surface thermal materials, all those technologies allow us to make a futuristic suit where you can just wear it, done. And children can wear it and not die from exhaustion. So this was my presentation about future of spacesuits. I hope you liked it, learned from it. In that case, please click the like button. If you didn't like it, didn't enjoy it, I would urge you to press dislike. Press this twice to show me your extra disappointment. Please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.